Okay, hello, this is Dr. James, and today I'm going to talk about how to build a 3D printed 2 millihenry to 12 millihenry variable inductor. I'll be using that for some of my experiments and taking some measurements with my network analyzer here, so it should be pretty cool, and some other devices. And we'll just measure the inductance and show you how to build this guy. Give the free STL files so you can print one out yourself if you want to build it. I'll put some of the parts in the links below. And let's get started. Should be an interesting project. Use this for some oscillators or other interesting things, electronic projects. It's hard to find these. You can't really buy these type of things, so you gotta probably build your own. And so I'll show you how to do it. Okay, let's get started. Okay, so today I'm going to talk about making a 3D printed variable inductor. And here's something that I designed in FreeCAD, and it's still got the support material on there. And here's a Ferrite core that I got from Amazon, I believe, and it fits right down the center like so. Oops. Okay. And I'm planning to attach it to a screw. I put like a little recess here so I can fit the nut in there, and should be able to screw this in and out. The screw's a little bit shorter than what I wanted, but I have another one. It's a little bit too long. I could try cutting this one off. I'm not sure which one I'm going to use, but I'm going to try to attach this ferrite core to the end of a screw, and then make a tunable inductor, hopefully. Should be interesting. Let's try removing some of the support material. Anyway, let me get this stuff off of here. We'll continue on with this building of this project. Okay, so here we go. Here is our form for holding our inductor, and I'm going to wind windings around here. I added a little bracket so you could bolt it onto something. So I guess we're into making our own components now. If we make a resonant circuit with something like this, then it'll be very efficient. Rather than using inductors to tune it, use a tunable, rather than using tunable resistors, which are lossy. This will have a higher Q and lower losses. Okay, so anyway, I got some special wire to wind this with, so we'll check that out. Okay, it looks like it finally arrived, and I think I know what this is. Let's open this up and see what's going on here. Okay, yeah, so I ordered, let's get it out of here, some fine gauge wire, because I wanted to make some maybe transformers or inductors for some oscillator projects that I'm working on. And I think this is about the finest speaker gauge wire that I could find. So I think I'm going to use this on this inductor thing that I'm building, and we'll test it out and see what kind of inductance we can get winding this on the spool. Okay, so let's, I guess, open this up and see if I can get this wound onto our spool here, and we'll do some measurements of the inductance to see what kind of inductance we get. Should be interesting. Okay, so here we got some electrical tape, and I think I'll just like to use this to hold our windings in place. Okay. And here's our spool of wire, and I'll just hold it down here, and I think maybe I'll just, to keep this out of the way, I'll string it through this hole if it'll fit. Okay, and I'll just start winding down here. And once I get a few windings on, maybe I'll tape it down with my tape that I saved here. Get the first layer taped down, and then this wire is a little bit thicker than I thought it was going to be. But anyway, I like to get the first layer taped down so it doesn't unspool while I'm winding the rest of it, because that's always a pain. And we'll try winding an inductor with this and see how this works. And if this is not the kind of inductance range that we need, then I think I might try a different size wire maybe, because this might be a little bit too thick for what I want to do. Okay, we'll see. We'll test it out. Okay, so I have this guy all wound up, and I think, let's see, oh, there we go. Here's our snippers. Let's just snip this. I'm going to think this is going to not be a high enough inductance for what we want, but let me go ahead and tape this guy down. Okay. And we'll just give it a quick test with the inductance meter that we have. And we'll try it with and without the core and see what kind of inductance we get. Should be interesting. And we can always put a different size wire on here, or I can print these out for free basically, so I could make another variable inductor. Use this one for a high frequency type application. Okay, should be interesting. Okay, so I have this inductor hooked up to my inductor meter here, or LCR meter. I can measure inductance or capacitance or resistance, and looks like it's not super high inductance, 6.2 microhenries. It might be good for high frequency stuff. Let me just try inserting the core into here, and okay, there. We'll see how the inductance changes. Okay, so it goes from was it about 6 to about 22 microhenries. I suspect that that's going to be a little bit lower than what I'm going to need for my project, so I might save this one just in case I need a high frequency inductor, and try winding one with a lot more windings, and maybe using magnet wire or something, you know, to get a higher inductance. And we'll see what we get out of that. Okay, should be interesting. Okay, just out of curiosity, since the inductance I believe should go as the windings squared, I put the two windings in series, since I just measured one winding before, and so this is no core inside of there. The core's out here right now. So now it's up to was 6 before, now it's up to 21. Okay, it's not quite the square of it, but okay, here's our inductor core, and we'll stick it in the hole here, and we'll see what we get. 21, 50, 70. Okay, so putting these in series, we get about almost 90, 87 microhenries. Not too bad, huh? Since I got some garbage on there. Okay, anyway, so I might try making a few other inductors and winding them with finer wire, so we can have I think I bought a bunch of these cores, so we should be able to make several of these. Should be interesting. Okay. Okay, so here's some, I guess this is 22 gauge enameled copper wire that I got off of Amazon. I'll probably post a link to that if you're interested. And I printed out a new form, and we'll be able to stick a lot more windings on this guy. So let's see what kind of inductance we can get out of this. I'm going to take off some of this resist here, this, for build material, and we'll try winding some of this enameled copper wire onto this guy and measure the inductance. Should be interesting, huh? Okay, so I removed all the support material, and let's just open this guy up. We'll see what we got here. Okay. I think there's a rubber band or plastic or something. I don't know. Oh my gosh. How do I open this up? Wow. Okay, there's a rubber band, or an invisible rubber band on that thing. Okay. Clear one at least. Okay. And, okay, there's one end of the wire. Where's the other end? Okay. Here we go. Okay, so I think I got freed up the wire here. And again, I think I'll just run this wire through this loop thing here to hold it while I wind it. And this is going to be something else. Not sure if I'll wind it all the way to the top. Usually, what I like to do after I get a row of wire like this, I'll put some electrical tape over it, maybe, to hold it in place, because I really hate that when I set the thing down and it all uncoils like a spring or something like that. It's so annoying. So I might need to find a better way to hold that spool too. See, just about slipped out of my hands. Anyway, I will not videotape this whole painful process of winding the coil, but usually I like to cover the inner coil with tape before I do the next coil, especially with thin wire like this, because if I don't, it will, like, the next layer will try to bunch into the previous layer, and it will not have a even winding, and it just cause a bunch of problems. So we'll see. Okay, looks like we're making good progress. A lot of times I like to cut a chunk of electrical tape and have it ready so I can just stick that on there and hold it in place if I have to go do something too, because usually this takes a while to do these windings. Okay, let me get to it. Okay, so here I have a piece of electrical tape that I pulled off, I cut off from using the wide electrical tape so I can cover more area. And here's our first row, and let me just tape this guy off. I'll probably put a second layer of tape on the bottom down here to make sure it doesn't unwind from the other side. And then we'll just start back winding more coils going back the other way. Okay. Should be interesting. Let's see, where's our razor blade? Lots of fun things. So, I'm interested in variable inductors because they have a higher Q, which means they have lesser losses in a resonant circuit, or if you're building an oscillator. Usually oscillators like to oscillate in a resonant circuit. And so, rather than using a variable resistor, which are readily available on the market, they don't really seem to make a lot of variable inductors, and they tend to be expensive and so on. Let's just wind back, I guess. There we go. We'll start our next layer of windings here. And I'll just keep on winding back and forth like that. And we'll measure the inductance and see what we got. Should be interesting. Okay. Okay, I think I found a better way to wind it. Just hold the coil down there and kind of use my two hands to wind it up here. So this is the end of the 4th row coming up. And I think I'll do a few more rows. And we'll measure the inductance. Should be interesting. Okay. Okay, so now I'm almost completing the 6th row. I'll do a few more rows, and then we'll measure the inductance. And if it's too much, I can just keep on printing these forms out. I can make one with less, but I'd like to see what the most inductance I'll get out of this is. So I'll wind it to the max this time, and then we can use that as a design parameter for if we want less inductance. Okay. Anyway, it should be interesting. So row 6. Okay, so I believe I'm coming up on the completion of row 8, and I do at least a couple more rows. And then we'll assemble this thing and test it out. Should be interesting. Okay, so there's the completion of the 10th row, and I think I'll just tape this guy off and finish assembling it, and then we'll give it a test. Okay. Okay, so here we have our hot glue gun. I'm going to try this first. It's not as strong as epoxy, but I'll try epoxy next. It's a lot more convenient. So here's our inductor and form all wound. And here is our inductor core. And remember, this is frequency dependent, so we'll take a look at that in a little bit. And here's a bolt. It's about this long. How long is that? 2 inches maybe. It would have been better if it would have been like 2 1/4 maybe, because then it would go the full length, but it's probably close enough. So let's just do this. I'm going to try to hot glue the end of this guy here and get them together before it cools down. Oh, may have to redo that. Okay. See if we can get this hot glued together, and if not, I'll just have to use epoxy or something because okay. Okay, so I guess that looks like it's going to stay in place. And make sure it's not overhanging too much so it binds up in our form here. Maybe I could cut it down with a razor blade. Okay, looks like it's staying in place. And I'll stick it in the hole here. Okay, and let me screw this nut down a little bit, and I'll just hot glue this nut into place as well. Try not to get the hot glue into the threads. Maybe I should have put some hot glue down inside first. Let's see if we can get some hot glue inside of there first. And we'll just stick our bolt down there and work it back and forth to make sure that it doesn't come undone, hopefully. And let's test our inductor to make sure it works. Should be able to screw it down to the end and see it when it comes out. Okay, there we go. I can see the inductor in there. Okay. Oh, looks like it maybe broke free. Okay, I may have to pull this back apart and work on it. May have to use epoxy on this. Okay, so let's see, we got some epoxy here. So maybe I'll just mix up a dab of epoxy to try to glue these parts together here. Where did they go? Okay. Let's get this out of here and we'll mix that up, try it out. Okay, and remember when you're mixing up epoxy, you want to mix it up really good. I mix it for several minutes. I've had things where if I didn't mix it long enough, it actually destroyed the parts I was trying to put together. It never cured and it melted them and all sorts of terrible stuff. But anyway, you want to mix the epoxy really good. This is a 5-minute epoxy. And mix it for several minutes. Make sure it doesn't set up, but okay. So here is my ferrite. I'll get some glue on that. And I'll put some glue on the end of this guy too. And I'll stick them together. And I'm going to actually, I think, cut a piece of tape. So I'm going to use the tape to hold them in place while they dry, hopefully. You know what I might do? Just to make sure it dries straight, because I'd hate to have this thing come out crooked and not fit in the tube, because that would be a tragedy. I could stick this whole thing in the tube and just have it hold it in place while it dries. Maybe that's not going to work. We'll see. I got to find a way to brace this so it stays in place while it dries. Okay. Okay, so I didn't want it to get stuck inside of our plastic form, just in case the glue got stuck in there. So I just took some paper and I wound it around it to keep it straight, kind of like a splint or something, and then taped it in place. And we'll see if it, I can always peel off the paper if it, I guess I put some tape on there too. See if I can find the beginning of this, peel it off. We'll see if this got glued okay. I want to get the tape off the threads because I want it to be able to travel the full distance when I'm screwing it in and out. Okay. Okay. Well, it still seems like the glue's a little bit soft. Huh. That's not good. Let's just, maybe it just needs a little bit longer to harden. Okay. Looks like it's holding though. Okay. Okay, so I guess it's looking pretty good. We'll just stick it into the coil form so we can do some preliminary testing on it just to see how it behaves. Should be interesting. Okay. Okay, so here we have the coil with the rod all the way inside of it, and it looks like we have an amazing 12 millihenries out of this guy. Okay, so that's screwed all the way in, so I'm going to screw it out then, and we'll see what the lower tuning range is of this guy, hopefully. Okay. Okay, so now we have this rod, so it's screwed all the way out, so it's in this section of the coil now, and it looks like it is 2.2 millihenries. Okay, so that's a pretty good tuning range. 12 millihenries to 2.2 millihenries Very cool. I think we should be able to make some interesting oscillators with this. And as I showed before with the lower inductance, we can definitely tune this to lower values by putting less coils on it. So with 10 layers, it goes up to 12 millihenries. I might be able to even put some more layers on to get it a little bit higher, but I think that's pretty good. Okay. Okay, again, this meter measures inductance at just one frequency, which is 1 kilohertz. And actually, the thing about these inductor cores is they're going to have a variable inductance versus frequency. So let's try testing at some different frequencies, and I have just the device to do that. We can see how the inductance varies versus frequency. That should be interesting. Okay, so this is the SAA2 Simple Vector Network Analyzer, 50 kilohertz to 3 gigahertz. And I set it on a range of 50 kilohertz, the lowest one, to about 10 megahertz. Let's see if we can get that in focus. And I did a calibration on this. You want to calibrate it with the Cal kit, and I showed how to do that in one of my other videos. And normally you don't care about inductance, so these traces are set to different values. This is a S11, this is phase, there's a Smith chart, and S21, which I'm not going to be using because I'm not going to use the second port. But what I'm going to do is I'm going to go into the menu here. I have a neat little pen so you can touch it. You can touch it with your finger too, but it's easier to do with the pen. And I believe it was display and format. And we'll go down to more options down here. And it has reactance right there. So we'll choose reactance for our first trace. Ooh, wow. Okay, and I'm going to hook it up to the inductive load, and we will see what the inductance is. Okay, right now we just have open circuit, so that's why it's acting a little bit crazy, and have it over a pretty big range, 50 kilohertz to 10 megahertz. So it's probably going around the Smith chart. So let's get it hooked up to our coil here, and we'll see what the inductance looks like. Should be cool, huh? Okay, so I think I'm going to have to recalibrate it because I calibrated it with kind of a short cable, and then I added this longer cable on it, and it looks like, since I'm looking over such a broad range, let's see, the transmission lines are coming into effect because at the very low end, let's bring our cursor all the way down here, it's saying about 14 millihenries, which is pretty close to what we were measuring with our other LRC device at 1 kilohertz. That's a 50 kilohertz, which is way higher. But then you can see on the Smith chart it becomes capacitive, and now it's saying picofarads. So due to this transmission line length, it's going around the Smith chart, and so we're not getting an inductive value because it was calibrated, you know, someplace down here. I actually took the blue cable out because I wanted to shorten it up, and it still wasn't short enough. So I think I might do my own personal cal right at the end here, and then we'll see if we can take out this transmission line length and get a better measure of inductance over frequency. That should be interesting. Okay, so I'm looking around for some resistors, and I happen to have this 2 watt, which is overkill of course for doing this measurements. So I'll just use these 2 of these 100 ohm resistors in parallel to get 50 ohms, because that's the impedance of our cable, and I'll just calibrate it right at the end of the clip leads, wherever they are. Okay, right here, and we'll see if we can get a better cal that will give us inductance over the range that we're interested in. Should be interesting. Okay, so let's try to do another calibration. So let's get back out of this menu here. go back to okay, so we have display, marker, stimulus, calibration is right there. And we'll do calibrate, and for open, okay, so let's try to do a new calibration here. So we'll go to our menu here, and go back to the main menu. So we have display, marker, stimulus, calibrate. Okay, and we'll do a new calibration, and the first one is open. Okay, let's see. Okay, we've already done it, so it's in black, but I'm going to redo it, and I'm just going to leave the clip leads open. And okay, so we'll try clicking on open. Okay, so it's going to take a measure at the open, and then I will short these clip leads together, like so. Okay, there, so now they're shorted together. So we will do a measure with short. Okay. And then I'll clip this load in between the two, and we will see how that behaves. It should be interesting. Okay, so now we have a 50 ohm load connected between these clip leads. And we will click on load here. Okay. And since we don't care about through, I guess we'll say done. Okay. And let's try hooking this thing up to our device now and see how the inductance looks. Should be interesting. Okay, so again, if I bring the marker, you can move the marker back and forth with these little buttons down here. If I bring it all the way down to the bottom here at the lowest frequency, it's saying about 12 millihenries. But you can see on the Smith chart it crosses over, so that's pretty close to what we were measuring on the other device. But as I start bringing the frequency up, we switch over to, due to capacitive effects, we switch over to picofarads. Anyway, but that's just due to the transmission line effect. Let me see if I can scale this so I can get the yellow trace on screen completely. Let me fiddle with this for a second. Okay. Yeah, because you can see it's going from inductance to capacitance at the very beginning here, that big slope down. Okay. Okay, so I recalibrated this at a lower range, only up to a megahertz, because it seemed like it was really doing goofy things. You know, the transmission line effects are really becoming a problem at 10 megahertz. And so I tried to scale this yellow trace. It's hard to move it around because it's not a normal thing that network analyzers usually do, and it doesn't seem like this one's very well equipped to deal with it. I had to slide it up because it's going from, since it's got some transmission line effects, it's going from inductive to capacitive right about at this frequency here, and that's just an artifact of the long cable length, relatively long compared to the frequency. So let's start at the lower end here. I have the cursor all the way to the left over here, and it looks like we are at about 13 millihenries. That's right there. You can see that. And I'm going to move the cursor up, so we're 15, 17, so the inductance starts to go up here at these, let's see what frequencies are these. These are like 78 kilohertz or so. It goes up, 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 so you can see the curve goes up, and then at 16, 14, so it's coming back down, and it's going to cross back into capacitance right about here, because it crosses the 0 line there. So anyway, that's just due to transmission line effects, but definitely you can see the inductance is changing over frequency. Maybe I should recalibrate it to, what is this, about 300 kilohertz, so we can look at this range a little bit better. 50 kilohertz to 300 kilohertz, which is where it crosses over into the capacitive. Maybe we can get a better look at this this curve that it's creating. So this is the inductance curve, and it's definitely changing versus frequency. Okay, very interesting. Okay, so I'm still having a little bit of problems getting this, let's see if we can get that in focus, this yellow trace to display, but so it definitely says 13 millihenries, which is very close to what we measured at the low frequency, and that's at 50 kilohertz. Should be 50 kilohertz, right? Right there. The frequency is 50 kilohertz, and 13 millihenries. And we'll move the cursor up, and what are we at? 14, 20 millihenries at about 77 kilohertz. Okay. And 25 millihenries at almost 100 kilohertz, 90 some kilohertz. Okay. And 50 millihenries at about 110 kilohertz. Okay, so definitely the inductance is changing versus frequency. And of course it crosses over on the Smith chart to the negative part. And so now it's capacitive, which isn't really real. That's due to transmission line effects. Okay, so anyway, there we have it. We have a 3D printed variable inductor, and some cool measurements with a network analyzer and some LRC meters here, LRC meters. And I think we can get a pretty good tuning range from about, at least at the low frequencies, 10 millihenries or 12 millihenries at the high end to 2 millihenries at the low end. And we can just tune it by twiddling this screw here. And anyway, okay, so here is a calibration over a smaller range, and let's take a look here. So I'm just going from 50 to 100 kilohertz now, and looks like at the low end we're measuring about 17 millihenries, and at the high end is about 14 millihenries. Just out of curiosity, what happens if I take the rod out? And now we're down to 2 millihenries. Isn't that very cool? So we have the rod all the way out here, and we're at 2 millihenries. And we insert the rod for 5, 6, 7, 8, 9, 10, 11, 12, 13 millihenries at 100 kilohertz. Very cool, huh? So it looks like our device is able to accurately measure the inductance of our wound coil, even if it's not plotting. I think it's maybe plotting the real part, so I'm not able to, for some reason, plot the imaginary part, so I can't get that line down, that yellow line, but you can read what it is. So anyway, very cool, huh? Anyway, there's how to build a 2 millihenry to 12 millihenry variable inductor. Okay, so we have our rod glued in place, and I'm going to try to glue this nut in place so I can screw it up and down. So I'm going to put some hot glue around the inside here, and hopefully I don't get it in the threads. Okay, and we'll shove that guy down in there, and make sure we can twist it. So I don't want to get the hot glue in the threads for sure. Okay. And we make sure we can twiddle this thing up and down. Oh, come on, really? Nice thing about hot glue is it's not super strong, so you can always pull it apart and redo it if there's a problem. Okay. Oh, come on. Okay, it looks like that nut is holding in place, so I think our inductor is good to go. Seems like there's something in the threads. I'm going to have to force it a little bit. Okay. I'll get that worked out, and we should be able to use this as a really high Q tuning device. Very interesting, huh? And this is Dr. James, and thanks for watching.